I'm a professor at Florida Atlantic University and in the Department of Ocean and Mechanical Engineering. And I would like to acknowledge my couple of graduate students, PhD student, Cassie Hoke, and master students, Angel Rosa Pagan, and they collaborated. And also would like to acknowledge support from 3Dure LE for the last year and a half or so for funding, and most of the initial sample preparation and research was sponsored by the FDOT, the Florida Department of Transportation. So let me go to the next slide. A little bit about background. Sorry about this. So here in Florida, we have a large number of inventories of bridges that are partially immersed. As you can see here, this bridge is close to our facility in Dania Beach. And this is about 60-something years old. And you can see that there are several columns that are in distress at this particular location. Interestingly, there is not much corrosion, at least visually, that is taking place at the tidal or above the tidal zone, rather is in the atmospheric section in this particular situation. So when you expose reinforced concrete structures to marine environments, like here we have in Florida, we have that this might be prone to induce corrosion once the chloride threshold has been exceeded at the rebar interface. So in the type of structure that I showed you a moment ago, the chlorides penetrate from one of the surface and go towards the rebar. And there is a geometric effect in some cases. But that location where you exceed the chloride threshold, and there might be some defects at the interface that might make it the location where it starts. And then this size can be very small, like a small pit in some cases. And then interactions with the surrounding reinforcement might determine how that corrosion propagates. There is some people that say that there is going to be some halo effect and some cathodic prevention due to the side that is corroding. And here in Florida, we use a number of the supplementary cementitious materials, as blast furnace slag, fly ash, and silica fume. They have been used for a number of years. So in this particular research, we look at these three SCMs in different, in some cases binary, in other cases ternary compositions. And we add this as a way to try to reduce the diffusivity of the chlorides going into the concrete. And in this particular research, we use two different types of specimens. Single rebar specimens are about 30 centimeters by 12 by 7.5, and they have a concrete cover of 1.9 centimeters. Whereas the others contain 3 rebars. Sorry, I forgot to mention for the single rebar specimens, the number 3 rebar was used, whereas for the 3 rebar specimens, a number 4 reinforcement was used. And in this case was a 30 by 30 top cross section with a thickness of 7.6 centimeters. And you can see that there are 4 compositions that were prepared. Some of them contain only black furnace slag in a ratio of about 50%. Others contain 20% fly ash. And then we have ternary mix 1 that contains both slag and fly ash. And then another one, T2, that contains fly ash and silica fume. The water to cementitious ratio for the first 3 were about 0.41, and the last one, T2, had a water to cementitious ratio of 0.37. And these specimens were subjected to electromigration. And we use a power supply, and we put some calcium hydroxide at the bottom of the containers that you see here, and a mesh as well of either stainless steel or titanium mixed metal oxide. And we apply potential gradient between a mesh that was on the top and that one that was at the bottom. And we didn't interconnect in any of them the rebar. So this is more like an RCP type of test where you are driving the chlorides from the top towards the bottom in this particular situation. And the potential difference initially was up to 3 volts. This was reduced if too much polarization of the rebar was taking place. And this was conducted for a period of time. And the samples, actually, the reservoir was placed about 2 months after the sample was prepared. And the number of days that you will see later are starting from when the solution was placed in the reservoir. And in this particular table that you see there shows you the amount of total ampere hours that were applied to each one of the single rebar specimens for a couple of the compositions that we're using here. So during this particular part of the project, we monitor the potential versus time. And something that I forgot to mention is that all these specimens were prepared in 2016. And then as part of the 3D LE project, we continue the monitoring, and we are reporting about 450 days that have been monitoring, but I'm including in here the earlier data collection that were collected as well. And the corrosion currents were measured using galvanostatic pulse. For the most part, they were about 10 microamps and about 200 seconds. That allow us to obtain both the potential of the rebar before starting the test, the solution resistance, as well as the approximate idea of what is the RC. And from there, you can obtain then the corrosion current. Since we don't know what is the area of the rebar that is corroding, we kept these values in corrosion current rather than in corrosion current densities. And the solution was periodically removed about 2 or 3 weeks at a time. And this was done about 8 to 9 times over the last 3 years. And this is to allow additional oxygen to penetrate into the concrete. Most of the samples are kept in a high humidity environment, greater than 85% relative humidity. A number of samples as part of the effort that of this project, we placed them in environmental chamber, and this is after IP and HOPE. And we placed them very low relative humidity and elevated temperature, try to dry them, and then we increase the humidity and the relative, and as well lower the temperature to 25. And we kept them in that chamber, and we continue monitoring similarly to what we do for the other samples. In here, we are also going to report the mass loss calculated by using Faraday's law. I'll describe in a moment how we integrate the corrosion currents to obtain the charge, and from there, the mass loss. So moving on, here is an example of the way that the rebar change as a function of time for the corrosion current on the left, and this is for a 3 rebar specimen. And in some samples, we observed what you see here, that the corrosion current decreased as a function of time. And Otieno has reported this, that he observed that type of behavior on samples that were also corrosion was initiated using an electromigration method, in slightly different from what we did here, but still comparable. And you can see that each one of the rebar potentials tended to increase, and these values are versus calomel reference electrodes. If you want to convert them to copper sulfate, then you subtract or add minus 75 millivolts, and that will give you the value in copper sulfate electrode. And you can see that we are reaching almost 1,800 days of monitoring, and this period that you see here, that I'm encircling with the cursor, you might or might not be able to see that, those last 450 days are the ones that were measured as part of this effort. In other samples, we have a slightly different behavior in the sense that in this particular specimen, you can see that the corrosion current increased, went down, increased again, went down a second time, did a third time, then have a decay and reach minimum, and more recently then we have observed that in some of them, again, they start increasing. So these might be indicators where we have this oscillation towards larger values, that additional sites are becoming active, or that maybe the corrosion area has increased, or likely a combination of the two. So that happened on both of them, and I'm going to use this particular plot on the left to describe how we obtain the mass loss. So each consecutive value was average of the two measurements, and we multiplied that by the time elapsed in seconds, and from that you can obtain the charge. You repeat that for each one of the pairings, and you can calculate the area under the curve in converted to charge. You use Faraday law, and from there you can obtain the mass loss. Interestingly, on the right, you see the potential, how it changed, and the potentials went towards more negative values, remain in the active environment. Then we dried the samples a little bit, left them, I guess, a winter without adding moisture, and the values went to more positive values, but then it have become more active again for this particular specimen. So for time constraints, I'm going to move a little bit faster. So in here, you see a sample that was actually placed into the environmental chamber, this T1 sample on the top left. And you can see that the blue symbols are indicating how the corrosion current changed as a function of time. And in this red bracket is when we moved it to the environmental chamber. And for this particular specimen, by doing that, the corrosion current decrease is still a value that you can measure, and that is comparable to the other sample that has the same reservoir length, but it has not become as active as it was before. And that you can corroborate that the potentials on the figure here on the right were more negative. For the T2 sample that you see here on the bottom, the symbols, the T21, the blue one, that one was not moved into the environmental chamber and had a behavior where there are a little bit of oscillation initially, it plateaued, and then it started to increase after 900 days, and it has been oscillating and relatively remain at a value of about 10 microamps. The potential indicates, again, similar or corroborating that was active. It became less active, if you will, by using a more or positive potential, but then it decayed again. In this case, the sample that was moved to the environmental chamber, the red one, when we did that, the potential went to more positive values after drying and have remained values more around -150 versus calomel. And again, the corrosion has not increased in that one. Just want to mention one sample in here, in this case for the AFA5 sample, very similar trend, it decay. We chose this one because it had an initial trend going increasing in here. That one was moved to the environmental chamber. But in this case, after an initial decay, the values actually increase to larger values than what were observed before. And so that's for the red specimen in there. And also for the SL, you can see here that we have similar oscillation to what I show you for one of the 3 rebar specimens, but not all of the samples are having this big performance. Some of them have the downward trend that I showed you initially, but not to be repetitive, I only chose one of them. So let me go and continue here and show you, we did this type of plot that tried to capture the first quartile and what is the average potential as a function of the reservoir size and composition. And you can see that the average for most of them are more negative than 300. So in general, most of them are active, but the values have spread over time And here we are not observing that in some cases, the more recent values might be the more positive. And the bottom plotting here have a similar type of information where you see the average corrosion current group for the 3 rebar specimens group per reservoir size. And that in some cases, there were some values likely at the beginning of the monitoring where the corrosion current was larger, although in some specimens, more recent values appear to suggest that they have become more active as well. These plots in here are showing the behavior correlation between the solution resistance that is measured and the corrosion current. And these 4 plots corresponds to the 3 rebar specimens. And we use the last 3 measurements for each one of the rebars. So each symbol corresponds to a rebar. And you can see that there is a couple of trends for the FA specimens, T1 and T2, but there is quite a bit of a scatter for the samples that are SL. So that means that for a given solution resistance, there is a range of corrosion currents that were observed. And this is the data that was measured between May and August of this month. So let me move to the next slide. In here, we have plots that correlate the corrosion current now on the x-axis versus the corrosion potentials, again, for the 3 rebar specimens. And in this case, there is 1 outlier for the larger reservoir size, but all others appear to be in good correlation, which suggests that those that have the more negative potentials are the ones that are having the larger corrosion current, which makes sense. But interestingly, there are samples with the smaller reservoir that are comparable currents and corrosion potentials than those with the larger reservoir size. On the other hand, for the SL, we have some of the samples that the rebars that are in the larger reservoir that actually have more positive values with the smaller corrosion currents. But you can see that there is a good correlation between the corrosion and the current and the corrosion potential. The trend is not as clear for the T1 and T2 rebars, but still there is a sense, again, maybe the slope is different compared to the FA and SL samples for these ternary specimens. And these are for the 3 rebar specimens, and this is the correlation that we observe for the single rebar specimens. In this case, on the top, I'm showing you for the FA, the corrosion versus the corrosion potential versus the corrosion current. And you can see compared to the previous plotting here, that is shifted to the left a little bit. So the slope is different. And that might be an artifact for the RS and also maybe the amount of ampere hour that was applied of each specimen. Interestingly, at the bottom is the RS versus I-core. In some cases, in this particular single rebar specimens, the RS that was measured, the solution resistance was significantly larger for the smaller solution reservoirs compared to those from the previous page. As a summary in here, and I'm not going to go after each one of them, but here is where we are currently as to what is the mass loss on each one of the rebars for the period between April and 2017 to August 2021, and by using the Faraday laws. What I want to point out that there is a case in which the mass loss is more than 1.3 grams, whereas the smallest was around 0.14. And research by Torres and Sagüez has suggested that as little as 0.3 can cause cracks. In this case, maybe because we have high moisture in our country is that we have not observed that. So we have outdoor samples that are experiencing cracks, and we are, and that's part of this project as well, but we don't have time to present that here today. To conclude, to keep in time, the corrosion propagation has been monitored for almost close to 1,800 days now. Part of about 450, 420 were supported by 3Dur LE project. And we presented correlations between I-core and RS and E-core and I-core for both 3 rebar specimens as well as the single rebar specimens. In some specimens, the corrosion current appears to be increasing over the last few months. The mass loss was also computed, and as I just mentioned a moment ago, it ranged between 0.1 grams and 1.34 grams. Thank you for your attention, and I would like to acknowledge, as I mentioned, the sponsors 3Dur, LE, FUT, as well as FAU.